So we are going to continue our discussions on the SRAM cell design. And in the last lecture, we stopped here. So in the read operation, so what we need to do is to pre-charge the bit line and bit line bar with VDD. And then you turn on the word line. So once you do that, then depending on the data pattern you store, for example, in this case, N1 is 0 and N2 is 1. So then on the left-hand side, this PG1 and PD1 will be on. And you will have the discharge current from the bit line to the ground. So here, since those two transistors are in series, you can approximate that as two resistors to the first order. So then this N1 node, is a voltage divider. And here, the idea is that during the read operation, you don't want the data to be disturbed. That means you want to maintain the zero state after the read operation. That means N1 needs to be 0 after the read operation. But during the read operation, the N1's voltage potential actually is raised up a little bit due to this voltage divider effect. Right? So you see here the current is flowing through the PG and PD. So then this N1 node voltage must be larger than the ground. So this is a very critical point. You want to make sure that this rise of the voltage is still minimal during the read operation, so you don't disturb the data. So in order to make that happen, you want to make this N1 voltage close to ground. To make that happen, this is voltage divider, so you know that for the PD's resistance, you want it to be small. So let's say the RPD smaller than RPG. So in that case, then the N1 node voltage can be maintained as low as possible. So to make the resistance small, that means what for the transistor? Any idea? To make the transistor's channel resistance small, that means the transistor's W over L is large, right? So because, let's say resistance, this one, so let's say conductance, G, PD will be larger than G, PG. And conductance is proportional to the W over L. So that means ideally you want W over L, PD larger than W over L, PG. So this is the indication of this rate disturb free operation. So you want to make sure that N1 node will not increase too much. So in this timing diagram, as you see here, right? So when we turn on the word line, and then the bit line start decaying, and meanwhile the N1 node, this N1 node voltage start increasing. But due to this requirement, we want to make sure the N1 node only increase a little bit, and we don't have this crossover. Then after the read operation, so you turn off the word line, then due to the self-recovery effect of the cross-coupled inverter, then the N1 will return to 0 and N2 will go back to VDD. So this is due to this mechanism here, we showed here. So this is because the noise is small enough, so then this positive feedback between the cross-coupled inverter can help recover the state to the original stable points. So you can think that during the read operation, actually this N1 node is somehow disturbed by it's not noise, but it's due to the operation, the N1 node voltage actually increases a little bit. After the read operation, when word line is turned off, then what is left is only the coupled inverter. So in that case, then due to this positive feedback, then the data can be restored. So any questions here? And here we define this W over L ratio as a beta ratio. So here we see the W over L of the pull down divided by the W over L of the cascade. We define that as a beta ratio. And the beta ratio you want it to be large to satisfy that requirement. Okay, so this is the sizing of the transistors for the read operation. And we can also consider the read speed. And to the first order, any delay of the circuits is due to the charging and discharging. So you can think the current through the cascade, like this current, cascade current, multiplied by the delay will be the charge you moved from the bit line. And then that will also equal to the capacitance of the bit line, CD, times the voltage change in the bit line. So basically, this is the charge conservation, right? The current flow multiplied by some time, let's say delta t, equals to the capacitance of the bit line multiplied by some change of the bit line voltage, delta v. So you can use this equation and then get the delay, which is delta t equals to capacitance of the bit line multiplied by the bit line voltage change, delta v, divided by the current flowing through the cascade. This current is going to discharge. So here the delta v is the decay of the bit line voltage. So that is actually the sense margin for the peripheral sense amplifier to sense. So typically you just need like 100 or 200 millivolts decay of the bit line voltage. Then the sense amp is able to sense this small signal difference. And the capacitance of the bit line is typically in this range, 0.2 femtofarad per micrometer. So it depends on how long the bit line is. So the longer the bit line, the larger the parasitic cap is. So that means for larger array size, then you are going to have larger bit line capacitance. And then you can use those typical numbers and run some calculations by yourself. But typically for the SRAM, like you want to sense within like 1 nanosecond, right? Like 1 or 2 clock cycle, let's say 1 nanosecond. The typical current flowing through the cascade transistor will be on the order of like micron amp or 10 to tens of micron amp. That is a typical current flowing through the transistor, like let's say around 10 micron in that range. If you want to do this within like 1 nanosecond. So, any questions on this slide? So I think this kind of equation is generally true for any digital circuit. For let's say, if you want to change, discharge or discharge some circuits, and then the delay of that charging and discharging is always given by this kind of formula. The capacitance times the change of the voltage divided by the current to the first order. Of course, the current is not constant during this operation. But to the first order, if you think this is average current, then you can use this. Okay, so then let's go to the write operation. So in the write operation, what you want to do is to flip the states. And let's assume that N1 initially is 0, N2 initially is 1. Now you want to flip this. So then you need to provide, let's say you want N1 to become 1 and N2 become 0. Then what you want to do here is to provide the 1 to the bit line, which you apply VDD here. And then bit line bar, you apply 0, ground. Of course, then you turn on the word line. So then this N2 load will change from 1 to 0, and N1 load will change from 0 to 1. Then my question is, for those two switching, which one happen first? Any idea? Let's say N2 change from 1 to 0, N1 change from 0 to 1. Those two transitions, which one happens first? Any guess? 0 to 1 happens first. So the truth is N2, 1 to 0 happens first. So let's look at why is that. So you look at this bias condition for this circuits. If you look at the N1 node, you look at this left-hand side, you will notice that this configuration is exactly the same as the read configuration, right? In the read, if you look at the read condition before, you have 0 here, and also you have VDD to the bit 9. So the left-hand side is exactly the same as the previous slide here, right? On the left-hand side, the circuits actually are exactly the same for the read or write. They're the same. So, as we just discussed, for the read operation, by design, you don't want the N1 node to increase too much, right? You want to maintain the N1 node volume to be small, close to ground. That means by design, the 0 to 1 transition will not happen, right? This is like the read operation. 0 to 1 will not happen. Then that means the 1 to 0 must happen first. So the 1 to 0 must happen first, okay? And to make the 1 to 0 happen, you look at the right-hand side here. So in this case, the bit 9 bar is ground, and you have the 1 in the N2. So PG2 is turned on, and the current flow is like this. And then the PU2 is also on. This is PMOS. PMOS, you know, here the N1 stores 0. That means here is 0, and this is the VGS for the PMOS. This is VDD. So PMOS is on. You know, PMOS, when the gate is 0, then the PMOS is on. So you have this kind of a path for the current flow from the VDD to through the PU2 and PG2, and then to the bit and bar, which is ground. So then you can again approximate those two transistors as two resistors. So you can still think that two transistors are like two resistors. And this is your N2 node. So now you want N2 to be as small as possible, right? Because initially N2 is 1. Now you want to have N2 become 0. Then you want N2's voltage to be small as possible. So that means this voltage divider, let's say the RPU and RPG, you want this kind of condition. Right? So basically you want the PG2 to be strong enough to pull down the N2 node from 1 to 0. And similarly we can do the conductance. You need to have this kind of condition. And then for the W over L, of course, you can do this. Right? If the W over L of the PU is smaller than W over L of the PG, then you can satisfy that condition. However, here I would say that even they are equal, you can still satisfy that condition. The conduction and let's say the conductance of the PU smaller than conductance of the PG. Even the W over L are the same. So why is that? Any idea? Any idea? If they have the same W over L, still that condition is satisfied. Yes. So you notice that PU and PG are different transistors, right? So the PMOS transistor, have smaller mobility than the NMOS transistor. So the pull-up transistor, even they have the same W over L as the pass gate, still they have lower conductance because the mobility mu P is smaller than mu N. Remember, mu P smaller than mu N. Okay, so this is the condition you need to satisfy, and once you have this condition, then the N2 node can be pulled down first. Now, if N2 node is pulled down first to be 0, you look at this. This N2 node is the gate to the PU1 and PD1. So this becomes 0. Then the PD1 is NMOS will become off. And the PU1 is a PMOS will be on. So if PU1 is on, that means you will have additional current from the VDD to N1 node. N1 used to be 0. And now you have additional current to charge N1 node. So previously you only have this path to charge N1 node. But as we discussed earlier, during the read operation, this charging current is not large enough to really raise the N1 node voltage. But now the PU1 is on, so you have additional current from the VDD to charge that N1 node. So those two currents add up together, so you have enough current to charge N1 node, and eventually N1 node will become 1. So those are two steps in this operation, essentially. So N2 needs to decay first before N1 can rise up. So to summarize here, this is the same figure as the previous one. And we just divide into the two steps. This is the first step, 1 to 0 transition happens first, and then 0 to 1. So to summarize here, let's say the 1 to 0 transition initiates the write process, because 0 to 1 transition is designed not to occur as the read operation requires. So you can also see this from the timing diagram from some real simulation. If you run SPICE simulation, you will also see this. Let's say this is the write operation, and we provide, let's say, the bit 9 to be 1, bit 9 bar to be 0. Exactly, we are going to switch N1 from 0 to 1 and N2 from 1 to 0. So you look at the timing diagram here. So after the word line is turned on, so the N2 start decreasing first. Right. The N1 increase very slowly until the N2 is decaying to here. Then the N1 start rising. So this crossover happens is somewhere below the half VDD. Right. So this crossover happens here because you need to wait till the N2 decay to this level, and then the N1 can rise up. So similarly, we can define another ratio, which is what this gamma ratio. So it's defined as the pull-up transistors W over L divided by the pass gate transistors W over L. So this is related to the 2 up and task 8. This is similar as what I drew earlier. So you can approximate those two as two resistors. And you have that voltage divider effect. And in this case, you want the gamma ratio to be small. So any questions?
Where does the time diagram split line bar will go back to VDD?
Oh, split line bar after the red operation?
Yeah.
Oh, this is, we are going to discuss that in a minute. This is the equalizer circuits, I mean, at the peripheral circuits, you need to do that. It's not with the cell, it's due to the peripheral circuits.
Thus we intended to make it back to.
Yeah, we are going to discuss that shortly. So, okay, so this is the right operation. And again, this is a comparison between read and write. So you can see here, the left-hand side, the read and the write will have the same bias condition. So that's why this 0 to 1 will not happen first. Okay, so let's look at the SRAM array. So far we only talk about the single cell, and then we have to extend the single cell into this two-dimensional space and then build this array. And we have many rows and many columns, so that means word lengths and bit lengths. And at the peripheral circuits, this is generic as we discussed before. So any memory circuit will have the row decoder and the column decoder and mux. And then after the column decoder and mux, for the SRAM, we have the sense amplifier to sense that delta V, like 100 millivolts. And then for the write operation, we need to have the write driver to drive the data in. And there is an unique circuits for the SRAM array, which is precharge circuits, or we call it equalizer, which answered your question earlier. So we're going to say that this is because the SRAM, when you look at the bit line, it has bit line and bit line bar, right? It's always complementary, bit line and bit line bar. So, but before you read, you need to precharge both bit line and bit line bar to be VDD. And this precharge is done by the precharge circuits. And that actually helps you to maintain the bit line and bit line bar to be VDD after the word line is closed. So we're going to see that in the next slide. So if you look at the detailed design, for example, the decoder is just a standard logic. I guess you have learned that in the logic circuit classes. So it's just a standard decoder. You have an n-bit address, and then you will decode that to the power n rows. And then before the signal goes into the array, typically we will have the driver here, because the word line sometimes can be very long, like tens of micrometer. So we have the precision cap, and then in order to meet the timing requirement, then to drive any capacitance from the digital circuit design point of view, you need driver, basically a chain of inverter, right? Then you can drive that node with certain delay. So you will have some driver, basically inverters, to drive that word line. And then at the end of the column, we will have the we can have the precharge circuits here, and then column mux. And the column mux, in this particular case, we can have each column to have its own sense amp and write driver. But we have to have a 2 to 1 mux here to select this is a read or write operation, right? If it's a read operation, then the column will go through the mux and then connect to the sense amp. If it's a write operation, then go through the mux and connect to the write driver. So you need to have a 2 to 1 selection. So let's look at some of the detailed circuits. This is the simplest SRAM peripheral circuits. Of course, today's design can be more complicated, but this is the simplest version. So first of all, for the pre-charge, so what you can do is to have the 3 transistors in this kind of fashion. Okay. So you have 1 transistor that couple here. That transistor couples the bit-and bar, and then you have 2 pre-charge transistors to the VDD, and then you have this PE as the enable signal to the pre-charge circuitry here. So if the PE is up, is on, then this 3 transistor can make the bit-and bar to be VDD. Because here this is connected to VDD, and this is also connected to VDD, and this coupling transistor couple bit-and bar. So only when those bit-and bar potential to reach VDD, then you don't have current flow in between. So that means you reach the equilibrium, or let's say stable state, right? If there's a difference between bit-and bar, then this transistor will have current flow, but eventually those 2 bit-lines will have the same potential. So you use this kind of circuits to equalize the bit-and bar potential. And this kind of circuits is also used for the DRAM, as we see later. So this is the pre-charge, or sometimes we call it the equalizer, because we equalize the potential between bit-and bar. And then the second dash box here is the column marks. So it's very simple. So just 2 transmission gate, and then you have the selection. And so the signal goes through the marks, and then can be multiplexed to the, here this is the SRAM, and this is the right driver. So this part is the SRAM, this one is the right driver. So basically you have this 2-to-1 selection through the marks. It's just a transmission gate. And then the SRAM here is a latch-based SRAM. Latch-based. So actually it's very similar as SRAM. So this is the core of the SRAM. So you still have that coupled inverter. And the coupled inverter is controlled by this transistor. It's like a source transistor to the ground. And this is controlled by the enable signal SE. And also the SRAM itself will have this equalizer pre-charge circuits here, just to equalize those 2 nodes as well. So those 3 transistors is the equalizer. So what will happen